Hello, my name is Kevin Yeamans, and today I'll be presenting to you on my senior project proposal for Engineering Management 404. I am basing this partly off of my actual senior design presentation for the School of Biomedical Engineering, for which my advisor is Dr. Juan Shi. And the title of the presentation I'll be giving to you today is called Probing Deep Tissue Injuries by Contrasting Tissue Stiffnesses Using Piezoelectric Fingers, all of which I will explain to you throughout the course of this presentation. So a little background, the problem statement which I want to address through this project proposal is a way to detect deep tissue injuries. Deep tissue injuries are a form of pressure ulcers that form bony prominences, typically on bedridden patients, and progress outwards towards the outer skin layer. By the time they reach the outer skin layer, they need surgical intervention in order to be treated. Currently, there's nothing on the market that can detect them before they get to the stage where they need to be treated by surgery. So the idea of my presentation is to create a device that will hopefully serve this target market and prevent unnecessary surgeries in the future. So the existing solutions on the market are far and few between. Currently in U.S. hospitals, the nursing staff will use a Munsell color chart in order to look at the hue of the skin around a bony prominence where a deep tissue injury might occur. A deep tissue injury presents itself as a purplish color by the time it reaches the outer skin layer. The problem is, as I said before, by the time it's at the outer skin layer, it is too late and it will require surgical intervention to get rid of. So the Munsell color chart only can positively identify a deep tissue injury, not do anything to prevent it. The other device on the screen is called an SEM scanner, which this is a handheld device that sends out waves to detect differences in bioimpedance in a human skin. This is promising, however, it is an extremely expensive piece of equipment that is also not cleared by the FDA, so it's not commercially available in the United States. On top of this, it's also extremely expensive, so if it ever is available in the United States, that's a barrier to entry for it, since hospitals will not want to be paying thousands of dollars for each individual unit. So for my project proposal, I want to use a technology that was developed at Drexel University in a new way in order to treat this underserved market. So the piezoelectric finger is a technology that Dr. Juan Shi patented while at Drexel University and was eventually taken and commercialized into the product seen on the screen. The product on the screen is called the eye breast exam, and it is used as an early breast cancer detection screening tool. And Dr. Juan Shi created the technology, and then she went through the technology transfer office at Drexel to work with an outside company to commercialize the device, and is now available in the marketplace. When she was doing her initial research, she was granted an $800,000 grant from the state of Pennsylvania in order to do her work. And then she was partnered with UE Life Sciences to make the device that I showed you on the previous screen. So the idea for my project is to take the patented technology that Dr. Shi has and the excess lab equipment that she has left over from the grant, and to use it to create a device that will use her technology in order to properly identify deep tissue injuries in the at-risk patients. So the way a piezoelectric finger, or a PEF, works is that it measures the elastic modulus of tissues in vivo. And so the way that it is able to do this is by having 3 layers, 2 made out of lead zirconate titanate, or PZT, and then a stainless steel layer. A voltage is applied on the top PZT layer, which causes the cantilever bar to bend. By knowing the amount of voltage applied and the distance that the cantilever bar traveled, you're able to detect the elastic modulus. And so the way that this works in the eye breast exam scanner is that it finds a localized region on the patient and is able to detect the elastic moduli of the tissue in that region, and is able to determine what is normal tissue and what is abnormal tissue. And the abnormal tissue can be, in that case, a breast tumor in its early stages. And that device on the market is over 95% accurate in early detection. And so I want to take that technology and its accuracy and to create the device to detect the irregular tissue near the bony prominences that would be correlated to a forming deep tissue injury. So the objective is to design a handheld device to facilitate the detection of deep tissue injuries before they require surgical intervention. So the solution that I'm proposing to you today is to take Dr. Wan Shi's piezoelectric fingers and create a housing for them in order to enable this application. Also, for process improvement, and since the PDFs are being made in Dr. Wan Shi's lab, I am proposing templates being made that will standardize the process of making the PDFs so they are repeatable and more accurate in that way. Also, Dr. Shi's PhD students for her breast cancer detection device created computer programs in order to manipulate the data that is obtained through the sensor. And so all I need to do for my project in regards to this is manipulate some of the variables in order to make it work using only the one sensor that I'll be using in my handheld device for detecting DTIs. So here's a schematic of the proposed device. As I said before, it has 3 layers, 2 PZT, 1 stainless steel, and then off of the stainless steel layer is a stainless steel probe. The bottom of the probe is called the contact area, and this is what makes contact with the patient's skin and enables the calculations for the elastic moduli. The outer border shows the housing that I'm going to create to protect the PDF during use. So here's some constraints and requirements for the project so far. The first 2 are constraints on the actual PDFs that were dictated by Dr. Shi's patent and are measurements on each device that are needed for them to function properly. The next 2 constraints are constraints of human anatomy for the areas where deep tissue injuries will be prominent, and this just dictates the depth that the device needs to be able to detect accurately in order to find DTIs. And the final constraint is about the accuracy of the measurements from the device. They must fall within 95% limits of agreement with a gold standard mechanical testing method. In this case, is a Bose machine that's in one of the labs at Drexel University. And this is just there to enable peace of mind knowing that the measurements from my device will be accurate and repeatable. And so what I've done so far, here is an example of an assembled PDF that I've constructed in Dr. Shi's lab using her leftover materials from the grant. Here is a CAD model of the housing design that I've created in order to hold the PDF during use. Here is it on a scaled model of a human and shown at a bony prominence, in this case being the heel of the patient to show its relative size. I made a rapid prototype of the first design of the housing, and so you can see that I have now a physical model of it, and I've put a PDF in it and secured it using a clamping mechanism, and it's very promising so far how well the housing I designed holds the PDF and used during the verification testing. Here is the template design that I've created in order to standardize the PDF creation process that I spoke about earlier. Here is the actual device being used in order to make sure that each PDF is made the same as the one before it. And so for verification testing, what we have done in the lab so far is to create 2 gelatin analogs, one that represents healthy human tissue and the other that represents irregular human tissue. And this will represent the 2 different things that the device will be detecting, one being normal healthy skin and the other being the deep tissue injury. And so here is a PDF testing on both of the different gels and recording the measurements on the oscilloscope in the background. And so we have gathered data from that, and then we use the Bose machine in Drexel Disk 304 in order to verify our measurements. And I'm happy to report that they've fallen within the 95% limits of agreement that we were aiming for, which means that the PDFs that we've created are accurate. So the societal impact of this proposed device is that it serves a target market that has no technology currently for them that can help prevent surgeries. And so this will be great use in the future in helping those patients. And so the next steps moving forward are that we hope to obtain funding with the project upon this proposal, construct the housing out of a more robust material. In this case, we chose PMMA, which is an acrylic, and then we need to set up, with the funding, human trials in order to test the device, make sure it works on people, and then to get 510K approval by the FDA. And then the final step will be to work with a company that, such as the one Wanshi worked with before, in order to commercialize this new project. Thank you for listening to my presentation, and please email me via the course communication system if you have any questions.